In this week's video, we will be talking about molecular orbital theory of heteroatom molecules. Heteroatom meaning two different types of atoms. First problem will be hypofluorite, OF-, has a similar structure to hypochlorite, ClO-. What is the bond order of hypofluorite, and is it dia or paramagnetic? So where do we begin? Well, the first thing that we must need to do is talk about the atomic orbitals of each atom. So the first thing we will do is draw the atomic orbital of oxygen. We know, based off of our valence theory, that we must start with our 2s orbital. Then we will also add in our 2p orbitals. Remember that there are three 2p orbitals. We must add our number of valence electrons. So we are going to add a total of 6 valence electrons. The next thing that we must do is label our atomic orbitals for our fluorine. Remember, they have the same valence orbitals, so once again we will have a 2s orbital as well as the 3 2p orbitals. Using the number of valence electrons, we must add 7 valence electrons. It's important to note that because of the negative charge, we are going to add a 7th valence electron to our oxygen. Now that we have the total number of electrons, we must start building our molecular orbitals. If we combine the 2s, we will get a sigma 2s and a sigma star 2s molecular orbital. Now we must combine our 6 combined 2p orbitals to form our molecular orbitals, and we will start with our sigma 2p molecular orbital. We will then get 2 of our pi 2p orbitals. And now that we have our bonding, we must get our antibonding. So we will now create the 2 pi star 2p orbitals as well. Finally, we will get our sigma star 2p antibonding orbital. On an exam, you will be given this type of diagram. Now, using the Aufbau principle, we must build from the ground up. We have a total of 14 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. We have filled our molecular orbitals with our valence electrons. So what does this mean for us? Well, the first thing that we should do is discuss the bond order. Remember, this is the number of bonding electrons minus our antibonding electrons divided by 2. So how many bonding electrons do I have? I have 2, 4, 6, 8 bonding electrons. For my antibonding electrons, I have 2, 4, 6. So I will take 8 minus 6 divided by 2 and get a bond order of 1. This is common for our various hypospecies. So the next thing that we want to do is discuss the para or diamagnetic species. Notice that both of my frontier orbitals, the orbitals farthest away, are paired. This means that we will have a diamagnetic species. It is important to note that if I had any unpaired electrons, it would have been paramagnetic. Our second problem for today is using the MO diagrams for NO, which of the following is most stable? NO, NO-, or NO+. What we need to do with this problem is start with our same plan, and that is with the atomic orbitals of our nitrogen first. Just like our last example, we are going to start with our 2s orbital. It also has 3 2p orbitals. Now we will start with the atomic orbitals of oxygen, these being the same orbitals but slightly different. Because oxygen is smaller, notice that I have put the energy slightly lower. So the 2s orbital and the 3 2p orbitals from oxygen are a little lower on the diagram. You are not expected to know this, and you would be given this on an exam. However, we can build the same molecular orbitals that we've done before. In this case, when we combine our two s's, we will get our sigma 2s bonding orbital, and we will still get our sigma star 2s orbital as well. Notice that the antibonding still has to be higher than the atomic orbital of our nitrogen. So now we work with our 2p orbitals. We will build our sigma 2p orbital and our 2 pi 2p orbitals. Finally, let's put our antibonding orbitals in. So we need to have our 1, 2 pi star 2p orbitals. And finally, the last orbital we need to put in is our sigma star 2p orbital. Seeing that we're dealing with 3 species with different numbers of electrons, this is why I have not put the valence electrons in. So let us go and get the total number of valence electrons for our 3 species. Our NO plus is going to have the fewest amount of electrons. This is going to be a total of 10 valence electrons. If I go to nitric oxide, it's going to have one more. So it'll have 11 valence electrons. And finally, NO minus is going to have 12 valence electrons with the final addition of the last electron. So first thing we want to do is start with our NO plus, has the fewest number. So we are going to populate our atomic orbitals to then fill our molecular orbitals. I have 10 total valence electrons, and I start to populate our molecular orbitals. Here are my 10 valence electrons in my molecular orbital. So let us determine the bond order for our NO plus species. I have 2, 4, 6, 8 bonding electrons. I will subtract the 2 anti-bonding coming from the sigma star 2s, and I get a bond order of 3. Now, because I have one more electron for NO, I'm going to add an electron to nitrogen. I could also add it to oxygen. Because it is now in a molecule, we can add it anywhere. If I add the 11th electron, it will now go into one of the pi star 2p antibonding orbitals. How does this affect our bond order? Well, we still have the same 8 bonding electrons, but now we have 2, 3 antibonding electrons. If we do 8 minus 3 divided by 2, you'll find out that our bond order is now 2.5. We've reduced the bond order by half of a bond. This means that it's going to be less stable. If I add the 12th electron, notice that I also have to put it in an antibonding orbital as well. So now, when I have NO minus, I will have the 8 bonding electrons, but now I have 2, 3, 4. When it comes to my antibonding, and this will now give me a bond order of 2. This means that this is the weakest bonding structure of them all. In this video, you've seen that even though you have 2 different atoms, you will still use the same process that were taught to you in the class. Good luck!